so welcome all to the webinar series in language technology. This webinar series is organized by the East Basque Center for Language Technology. My name is Eneko Aguirre. I am the director of the center. And this seminar is organized in conjunction with a course on deep learning for NLP and also a master program on language technologies, which we host in our research center. So this webinar series has been going on for 2 years now. You can see the several people, and just a short note to let you know that the recordings are available in the URL that you can see there. So it's a honor that today we are hosting Dan Roth. I'm really excited and thankful for Dan because I know how busy he is to take the time to explain to us. I'll do a very brief introduction. Many of you will know Dan already. He has several recognitions. He's a Eduardo Glan Distinguished Professor at the University of Penn, and also a lead of the NLP science at Amazon AI. And he's a fellow of not one, but four researcher associations, TacoLM, ACM, AAAI, and also ACL. And he has been awarded the John McCarthy Award, which is the highest award for the AI community. And many other important things about him, but I think it's best that we hear what he has to say about the time to reason. Okay, so I'll stop sharing now.
Okay, thanks a lot, Eneko. So let me try this again. Hi, everyone. I'm trying to share again the right screen. So let's see. Sorry, not yet. Does this work?
Yes. Yeah, it's perfect.
So you see my big screen. Okay, great. So I don't see anyone. So I'm going to ask you a question though. So please feel free to unmute yourself and talk to me. So first, thank you very much for inviting me. I want to talk about something. I call it here, it's time to reason. And not only because I think that it is time to think about reasoning in natural language processing, but also because many of the examples that I'm going to give as a way to argue that we should reason are about time and how to reason about time in natural language. So let me start by something that we all know. AI is in the news. The success of deep learning has made the media very, very active with respect to AI, and we can read in the news things like, AI is better than humans in question answering, in various other things. I'm sure you've all seen this, and on one hand, it's very exciting. On the other hand, I think it's a little bit scary because I worry that not only the media, but sometimes even us, we misinterpret what we can and cannot do. So the goal of my talk is going to be actually to discuss this, argue that there's a long way to go. And only part of my talk is going to be technical. Hopefully, it's going to be a talk that brings up a lot of questions to more than answers. But I'm going to use this as a starting point and try to argue that actually we have to qualify the success that we've had if we really solved question answering. And I'm going to start this with one of the examples that was in the media in the previous slide. This is an AI2 Aristo project that is actually very, very nice. It deals with science question answering and made really very, very nice progress on this very difficult data set, which my group has always also been involved in this. so I can appreciate the results, getting something like 80% on these kind of questions. So I'm going to give you an example of the type of questions there. Question: the rate at which a wave passes through a medium is known as its, and you have 4 options, and I think that we all agree that the right answer here is speed. Now, the system doesn't only get the question and the answer, but rather it also gets some context for each one of the options, because the idea is that the system is not expected to know everything off the top of its head, but rather it should look at relevant context and reason about it. And indeed, you see that the results are very good. So I show you results for 2 systems, Roberta-based and BERT-based, and in both cases, the results are very good, and the system is very confident about the result. However, we can play a little bit to understand what exactly is happening here and to what extent this system really understands what they're doing. And the first thing you can do is you can try to say, let's eliminate the context. And the expectation is that the results are going to drop significantly, because without the context, how would the system know? And when you do this, you see that, well, the results drop just a little bit, which means that the system actually knew the answer ahead of time somehow, and the confidence also drops just a bit. Now, if I bring back the context, but I trivialize it, and by trivializing, I mean, I'm going to take the second competitor, the toughest competitor to the right answer, in this case, amplitude, and I'm going to trivialize it. I'm just going to put the question again as the context. So the expectation now is that speed is going to win easily because there's no competition. So the confidence is going to grow and the performance is going to go up if I trivialize the other competitors. It turns out that the opposite is happening. So in fact, once I trivialize the context, actually the confidence goes down significantly and the performance of the system goes down significantly, which means that putting the question as the context actually confuses the system, which is very different from our expectation. I'm going to confuse the system even more by copying the question as the context many, many times. And the results are even less expected, because clearly there's no competition now to the top answer speed. Nevertheless, the system is a lot less confident. It thinks that amplitude is a good option here, and the performance of the system goes down. So the current systems, and this is something that you can repeat in several other tasks and contexts, and I want to think about it as the expectations that we have from an intelligent system. So if the system is really intelligent and it can do QA well and it can beat humans, we can develop some expectations for what else it can do. And what we show here is that the behavior of the system is very different than what we would expect. And as I said, this is true not only in this case. We've done this kind of experiments also in the case of spatial reasonings, where I show a sort of a figure here. The idea is to look at a table with blocks and sort of give instructions to a program to choose one of the blocks and place it somewhere else on the table. And you see that on the data set, or something that is very similar to the data set, the systems are doing very, very well, only that when you change the configuration a little bit, enlarge the table, shrinks the table, add some other blocks that are irrelevant, you do various things that are very, very simple and trivial, the system do not behave according to our expectations, which basically means that this is at least one signal that we are not there yet. And with this introduction, I'm going to show you this slide, and I want to ask you to try to read it. And please unmute and tell me what you think is written here. Any guesses?
First one is nice.
Nice to meet you.
Nice to meet you. Nice to meet you too. Excellent. So you see, this is something that took most of you a few seconds. Some will take a minute, but people can do this. People can do this reliably and quickly. And frankly, it's not clear how, because this is a really difficult task if you think about it. Right? You have to identify the units. You have to consider multiple representations. There's pictures, there's text. The layout is important. The spelling is important. Some phonetics issues are important here. Each one of these components that you identified here really means multiple things in isolation. But when we put it all together on one slide and you know that it means something, because I asked you a question about it, it's very easy for most people to very quickly determine what is, I think about as the best global interpretation here. And you know, this is something that is difficult, yet people do it very quickly. And if you think about the computational problem underlying this, it's really trying to assign values to multiple variables while accounting for interdependence among them. And I think that this is one good way to think about natural language understanding or decisions that we are making in natural language understanding. These are often a combination of many local predictions that could be driven by different models trained in different ways, different scenarios, different conditions, along with the ability to put these predictions together in a coherent way based on some knowledge that guides our decisions. Decisions that have to satisfy some expectations that we have from the output. And really, knowledge and expectation are really key here. So of course, the programs that we have in natural language understanding need to do a lot more than that in order to understand and communicate in natural language. But I think this exemplifies already some important aspects. One is that there is some notion of discrete reasoning when we think about language, because we kind of identify these symbols and thought about them in a discrete way. And that understanding, at least some level of understanding, can be thought about the best interpretation that we can give. Of course, this example brings up another important question, which is, how do we train for these kind of tasks? You cannot imagine training directly for the whole task. We typically will train component-wise, one way or another. So we used to think about natural language understanding, or at least I used to think about it as something that combines kind of two components. One of them I will call ambiguity, and the second one is variability. Where what I mean by ambiguity is that everything you say in language could have multiple meanings when you move to the meaning space, if you want. And variability, by variability, I mean that whenever you want to express some meaning, there are many, many different ways, variable ways to express them in language. And you know, I'm just giving here some examples that will think the same way about what ambiguity on the right side means. The fact that Chicago, for example, just a simple entity could mean so many things: a font, an album, a band. And I don't even mention here the key meaning of Chicago, the city. And on the left side, what I mean by variability, you know, if I want to determine if Jim Carpenter works for the government, it can be expressed in a very, very simple way here. Jim Carpenter works for the US government, but it can also be expressed as Russian Interior Minister Evgeny Topolov met yesterday with his US counterpart, Jim Carpenter. So the way we express things could be very, very different. And these two issues collude to make natural language understanding very difficult. Now, over the last few years, with progress in machine learning and NLP, we actually made a lot of progress in addressing these two challenges. I think more with the ambiguity than with the variability. However, we're not done, because if we want to think about decisions that depend on natural language, these really require reasoning abilities. And the example I've given before, and many examples I'm going to give in the rest of the talk, illustrate this. And sometimes it's useful to think about it as symbols. So what I'm going to argue is that in many cases, this reasoning cannot be accomplished by evaluating a single model, and we cannot even train directly to accomplish it. And I would argue that at the heart of this understanding is really a planning process that determines what modules are relevant, what knowledge needs to be accessed in order to support the decisions. So we need to think about decomposing questions or problems, composing them together, and do some planning in order to decide what's relevant, what needs to be accessed. And I'm going to try to give a range of examples from compositionality to the use of knowledge to how to put things together, and hopefully talk also a little bit about supervision challenges in this space. So let me start. And by the way, feel free to stop me and ask questions as I go. I have multiple talks here, so I don't have to necessarily complete everything. So let me start with my first example. And it's a simple question: will we make it to the movie? But notice that this is a little bit different than the type of question answering that we typically address. The answer is not written anywhere. You have to think a little bit about how to answer this. And basically, you need to know what is the time now. You need to know when is this at the beginning of the movie. And you need to figure out how long would it take to get to the movie. And now that you know these three, it's a simple computation or simple process in order to answer it. Now I'm going to change the question a little bit. Will we make it to dinner before the movie? And you would notice that really the reasoning is the same kind of reasoning. It's essentially the same question. I still need to know the time now. I still need to know when the movie starts. I need to know the time to get to dinner, but probably I also need to know an estimate of the duration of dinner. How do I know this? And perhaps there are some hidden events that I need to think about. Or what about parking? If I'm going to drive there, maybe depending on the parking availability, I have to decide whether I have time to go to a fancy Japanese dinner or I have to go to fast food. And so I need to do a little bit of planning here in order to set up the reasoning problem and to decide how to estimate the components here. Some of them are explicit in the question, like the dinner, the movie, and some of them may be implicit, like parking. And of course, I can make this as complex as I want. Will we make it to the movie after the game? So you have to know something about the duration of the game. And maybe I will change it from the movie to a movie. But you notice that in all cases, the reasoning is the same. All these questions are the same. I need to figure out whether the end time of the game or the dinner is before the start time of the movie, a specific movie or any movie. And clearly compositionality is really important here because you can see that there are multiple components here, some explicit, some implicit that you have to think about. And in order to really think about what models should I train, what models should I have in order to solve this reasoning problem, I need to be able to decompose. So compositionality is really important here. But also planning is really important because I need to know which questions to ask as a way to answer these questions. So let's move to my second example. It's still about dinner. So imagine that you're talking with an agent. This could be Alexa or Siri or Google Now, your favorite agent, and you want to consult the agent about dinner. So the agent would ask you, where do you want to go? I really enjoy Mexican food, but not when it's spicy. So the agent would say, how about Mexican restaurant with plenty of non-spicy options? Yep, is there one in Philadelphia? Here are a couple of good options. And the agent will continue and provide some options for you. By the way, this is not possible today yet, even though many people are working on it. But if we think about an abstraction of this very short and simple conversation, you can think about it something like this. So we are looking for the existence of a restaurant of a Mexican cuisine in the city of Philadelphia. And it has to satisfy some constraints. So the restaurants have to have menus. The menu has to contain some dishes. And we want that there will exist a dish that is non-spicy. Now, of course, it's not going to be as simple, because notice that some of the vocabulary that I use in this abstraction isn't even mentioned in the text. So I need to think about this as output of learning models, right? So I'm putting this in kind of red brackets to indicate that all the predicates and the constant that I'm using here are really output of learn models, right? So we will use neural embeddings because the predicates and the functions are really learned concept. Nevertheless, this example shows that somehow I need to be able to put these things together, incorporate some constraints. Many of them are going to be declarative, or at least soft declarative, and only then I will be able to kind of reason about this situation. So really we're thinking here about symbols one way or another, and you know, in the last few years, many people started to think about symbols as an evil invention of old AI people. I would argue it's not, because language is really a symbolic system. Any way you think about it, look at any pieces of text. I'm putting here a few pieces of text from various domains. Touchdowns, 96 yard, 10 million, challenges. All these things are really symbols that we have to think about and reason about. So even though we communicate via speech, gestures, writing, these are all continuous, the symbols are important because they are invariants of this communication. You know, even the desk that I'm sitting on now is, you can think about it as an invariant of a lot of things, but it's important that we call it a desk, and now we can do things with it and reason about it. So of course, many people have talked about it before, and I'm kind of giving here an example of 3 books that I think are really, really interesting in this space. So one of them is Yuval Harari in the book Sapiens, that I highly recommend, talks about the ability to assign symbols to things and reason about them as the key to the human cognitive revolution. Kripke, a very famous philosopher, wrote a lot about naming and thinks about naming things as key to communication and to cognition. And the third book that I mentioned here, which I highly recommend, is called The Enigma of Reason. Really thinks about reasoning from a developmental perspective, but also thinks about kind of this space of reasoning is about giving reasons, which basically is discretizing things and arguing about them. So if we are talking about this space of reasoning, I can introduce the guy here on the right. I'm sure many of you know who this guy is. If you don't know, this is Aristotle. And Aristotle founded a syllogism, a method by which you know, known information can be used to prove a point. So if we think about Aristotle, I can ask the question, did he have a laptop? And I'm sure many of you are smiling now, because a funny question. Of course, he did not have a laptop, and you know why, and you can explain why. By the way, if you go to Google and search for it, the answer is going to be yes, because there is a book that is called Aristotle's Laptop, so he must have had a laptop. But really, in NLP, we think a lot about these things, but typically, when we ask questions, even in the scenario of, say, multi-hop question answering, where we agree that we have to break down the question to multiple components, typically we are given the variables that we have to reason about. But in natural situations, what are the variables to reason about? Who really asks the questions? So even when I ask you, will we make it to dinner before the movie, the components were given to me. And all we had to do was to figure out how to estimate them and how to put them together. But in this case, I'm actually asking you a question. I didn't give you the components and how to decompose it, yet I'm sure that all of you thought about, well, we need to know approximately when did he die. We need to know approximately when was the laptop invented, and we need to know the order of these events. How do we do this? I mean, so how do we determine the strategies on the fly? And of course, how do we train for this? How can we supervise for these very, very sparse events that we encounter all the time? So in this context, I want to point you to a recent paper where we developed strategy QA, a data set that addresses these questions of kind of dynamic implicit decompositions. No solutions yet. And by the way, the solution to this, I would not count a system that says yes or no with some probability as a solution. I would only count as a solution a system that gives me also the explanation, the decomposition that I show here, or one legitimate decomposition for why the answer is yes or no. So as I said, Aristotle said that all beliefs come from syllogism or induction. By syllogism, he meant reasoning. And we may need to extend Aristotle's notion of reasoning a little bit. But the first thing I want to argue is that there is a lot more to cognitive behavior than just induction. Now, induction in itself is a very deep and important notion. And over the last, almost 50 years, the community has studied this quite a lot, and we've solved some of the mysteries. For example, the notion of generalization is not a mystery anymore. We have theory for this. We have mathematical theories. We understand how to measure performance. We understand the issue of same distributions, and we know something about, computational feasibility, error control, and so on. But we haven't done a lot in the space of reasoning, which is also a major component of cognition. And really, it's essential to make advances in this space also to support larger leaps, deal with the sparser situation that I've given already some examples for. So we need a unified formulation of learning and reasoning so that we will be able to account for acquiring and incorporating the appropriate knowledge, to figure out how to put things together, to deal with inconsistencies. And of course, this is not the first time that people discuss this. In fact, my PhD thesis 25 years ago or so was called Learning to Reason, where together with Ronnie Hardon, we actually showed in a formal way the advantages of joint learning and reasoning. You can think about it as what people call today end-to-end systems. But there's also a need to think about decoupling learning from reasoning. When do we need to do this? When do we have to decompose? And how should we compose? And how should we incorporate knowledge? So a lot of the rest of this talk is going to focus on these kind of aspects and try to suggest some directions of thinking about it. And the first one is that knowledge is really important. So I'm going to ask you a question. In Yokneam, in what months of the year is the longest day? And I'm sure that you don't know the answer. But I'm also sure that you have a plan for how to answer this, because you know that this depends on Northern Hemisphere or Southern Hemisphere. And if I tell you where Yokneam is, it's there in the Northern Hemisphere. Now you know the answer. So the question might be very difficult to answer. The answer is probably not written anywhere in an explicit way, but you can easily develop a plan that depends on some knowledge. You need to know that this depends on Northern versus Southern Hemisphere. Now, I could ask you a question in New York State, in what months of the year is the longest day? The answer to this is probably written somewhere. Or you can use the same type of reasoning that I illustrated earlier. Now, what's interesting is that if I change this to Boston, you know that the answer is going to be the same. If I change Boston to Melbourne, you know that the answer is going to be different, but you're not bothered by this. But if you think about our theories today, we really don't have generalization theory that explains this. And the reason is that these examples are not similar. And generalization today on the learning side really depends on some notion of similarity. But these examples are similar, modulo some knowledge that we have. Again, we don't have good theories for this. Now, notice that the relevant knowledge is out there. You know many, many things about New York, Boston, Melbourne, but very quickly, given a question here, you figure out what is the relevant piece of knowledge to answer these questions. And how do we do this? That's another mystery. And the last component that I want to bring up here is that if I give you these questions and answers, you cannot learn directly from these examples. You need some piece of knowledge, some additional piece of knowledge that will allow you to learn from these examples something. And again, this is something that we have to think about how we do. So knowledge is key, not only in order to answer questions as before, it's key also to know how to decompose the questions and consequently what to learn and how to learn. So I already asked you this question, whether Aristotle have a laptop, and it was clear that the answer is no. And it was also clear that this is a question about time. So it's a temporal question. I can ask you other questions. I can ask you, did Bill Nye vote for FDR? And I'm sure that no one knows the answer, but I'm also sure that you know how to get to the answer. You can just Google FDR, you can Google Bill Nye, and the answer is going to be no, because FDR ran last for presidency in the US in 1944, and Bill Nye was not born yet, so he did not vote for him. So it's still a question about time. But I can change the question a little bit. I'm going to skip this and I'm going to ask you, did Yitzhak Rabin vote for FDR? And this is not about time, because he was old enough to be able to vote for FDR, but he wasn't a US citizen. He was never a US citizen. And again, this is something that you can easily do with a little bit of planning and a little bit of search if you want, and reasoning over the results that you have. It's not about time, it's about, the legality of when people can vote and when they cannot vote. The key issue is that I want to point out is that you need to know something in order to figure out what are the dimensions or the aspects that are important here. And you really need to do some planning. You need to develop a strategy. So this is the reasoning process that I'm talking about. And again, I'm bringing up this data set of strategy QA, and they need to be able to come up with the explanation, if you want, in order to answer this question. So yes, no is unsatisfactory here. So, okay, so in fact, I'm going to skip this question because I see that I'm running low on time. And I want to move to other aspects of knowledge, and specifically, I want to talk about time. So with the background of will we make it to dinner before the movie, what do we need to do? We need to be able to do at least two things. One is to be able to estimate some things. How long is dinner, for example? And of course, we have to be able to put things together. So I want to talk a little bit about this acquisition process of how do we know how long things take? How do we know what is the typical time of things? And I want to talk about a series of works. I'm going to talk about it very quickly, where we are trying to do this, to basically acquire the common sense knowledge required as components of this type of reasoning. How long things take, and what you can see here in these figures is some of the outcome of this research. When we try to figure out order of things, typical time of things, duration of things, and then I'm going to attend to how to put things together. So let's see. Yeah, I think I can start talking about it. So I'm taking a detour here to talk a little bit about time in more details, and specifically temporal common sense. So people are very, very good at this kind of things. And if I want to be able to answer a question, Dr. Porter is taking a vacation versus Dr. Porter is taking a walk, everyone will know that the one on the left is going to take days, the one on the right is going to take minutes, and therefore on the left he will not or she will not be able to see you soon, and on the right she will be able to see you soon. So this information about time exists everywhere all the time, even though it's not explicit. So even when you read a story like this, my friend Bill went to Duke University in North Carolina with a degree in CS, he joined Google and so on. There's no time mentioned here explicitly, but if you think about it, there's a lot of temporal information here. We know that he went to college, so it's about 4 years, probably started when he was about 18. We know that he was in North Carolina for about 4 years. We know that he was in North Carolina 4 years, but Duke has always been in North Carolina. We know that he joined Google probably after he graduated, and so on and so forth. Many, many things that we know about time that are hidden in this story. So how do we try to start making progress here and identify these things? How do we develop this ability to know what is the typical time of things, what is typical duration, and so on? And we've made over the last few years 2 efforts in this. One is developing a data set that drives the challenge of reasoning about temporal common sense. And the second one is the acquisition process of duration, typical time, and frequency. And I'm going to say something about the data set. It's a data set that we call MC-TACO for multiple choice temporal common sense. A relatively large data set that addresses 5 dimensions of temporal common sense: duration, frequency, typical occurring time, stationarity, and ordering. I want to say one thing mostly about the methodology, because I think the methodology of evaluation is really important here. So here is an example of a question. He went to Duke University. How long did it take him to graduate? And there are 4 options. 2 of them, I think, are correct, the green ones. 4 years and 3.5 years are plausible. So if a system will answer just 4 years and will say that 3.5 years is the wrong answer, I do not want to take this as a correct answer, because I think that that could be luck. A system should be able to answer correctly by choosing both 4 years and 3.5 years, because both are plausible. So the exact match in this case is the right way to think about it. The F1, which is giving partial credit, is wrong, because it basically doesn't measure the understanding of the system, of what's happening here. Indeed, if you look at results, you can see that with the exact match, the gap between human performance and system performance is huge, about 40%. If you use the F1, it closes the gap, but I think this is not right. We have to be more careful in how we measure performance. This goes back to the first example that I mentioned at the beginning. You know, the brittleness of this system gives us, or not thinking about the brittleness of this system gives us sometimes the feeling that we are doing much, much better than we are doing. But I think it's important to attend to how we measure these things. So, so this is the data set. I'm giving here a few examples of questions, but I'm not going to spend a lot of time. I want to explain what is stationarity. I think all the other dimensions are self-explanatory. By stationarity, I mean that Paul Simon is in New York. Let's go see him. We know that Paul Simon is in New York today or this week, may not be there in 2 weeks, or was not there a month ago. While the Empire State Building is New York City means that it was there all along and will be there all along. So we have to be able to make these kind of distinctions, and some of the questions in the data set address these dimensions. So overall, it's a very difficult data set. The results are very bad, and very few people are working on this data set because it's difficult. But I encourage people to start thinking about this because it forces us to think both about the composition and the type of knowledge that is needed in order to be able to reason about it. And again, I'm going back to the will we make it to dinner before the movie, because this is a typical aspect of this. So now that we have this data set, the question is, how do we think about the components? How do we make this estimation? And how do we do this with minimal supervision? Because it doesn't make sense to supervise for these kind of common sense things. So we've developed an effort that allows us to develop some distributions over various common sense dimensions, temporal common sense dimensions. And I'm giving here an example of the output of the system. For Dr. Porter is taking a walk, the blue curve, versus Dr. Porter is taking a long vacation, the orange curve. What you can see is that we develop a distribution over temporal units, seconds, minutes, hours, and so on. And we show that the blue one is centered more about over minutes or hours, and the orange one is more days, weeks, and even months. So how do we do this? So the key idea is you have to be able to use the context, and you have to be able to use some kind of joint modeling, because people do not typically write how long it takes them to brush their teeth, for example. But they will say, I brushed my teeth in the morning, or I brushed my teeth in the shower. And if you model jointly multiple events, you would be able to eventually figure out approximately how long it takes one to brush one teeth. And similarly, I'm showing here a graph of I move my chair, I move my piano, I move to a different city, and the distribution that our systems manage to induce over them. So how does this work? I'm going to give a very sort of big picture. So the idea is to develop a language model that is time aware, and standard language models are not time aware. So if we want to be able to eventually get to a joint mask language model, the idea is that we're going to enrich the text with simple information extraction before we do the language model learning. And we basically use high precision patterns to acquire temporal information and overcome some reporting biases. Once we do this, we can basically learn joint mask language model. And we've done this in two settings. We actually did mask language models, and we've also used T5 with exactly the same type of data for the pre-training, and got a time-aware general BERT or time-aware general T5. I'm going to skip the details here because I see that I'm really running out of time, and I'm going to jump to, oh, you know what? Okay. So basically what we get as the data, is some kind of a annotation like this, where I played basketball, and this is the event that we have, and we have a separator, and then we have two special tags, the duration and the time. The duration is one of the aspects that we have. We have 5 aspects, and then we have the time. And one of the key issues that we are doing here is that we change the masking, and we actually mask full events. For example, in the sentence below, when we talk about I had a cup of coffee, where I want to be able to identify the type, as I said in the example, duration. It could be frequency, or it could be typical time, and the constant itself. A standard masking is going to allow me to predict that if I see I had a cup of, I will predict coffee. But what I want to be able to predict is I want to be able to predict time. So we are masking all the I had a cup of coffee together, and I want to be able to predict the time. And this is how we derive these distributional graphs that I showed before. Okay, so there's more details here that you can go to the paper too. But the important thing is that with this, we are able to develop these kind of graphs for a range of dimensions of common sense reasoning. And now the question is, sorry, I'm skipping again these details. is how to put things together. I want to say two things about putting things together, and I'm going to do both of them in the temporal domain. So the first one is basically using relatively old technology in a new context. The idea is that I want to be able to reason about events, and I want to think about order of events. This is kind of the basic question in will we make it to the movie? And this is the basic question in many of the examples that I've given before, including the Aristotle. It talks about order of events. So if I think about identifying events and then thinking about ordering them, the problem is very, very difficult because even in this specific, very simple piece of text, I have multiple events and I have to reason about the relations, the temporal relation between all of them, order n square edges in this graph. And it's difficult even for people. People typically, when you ask them to annotate it, will only annotate partial graphs. However, it's not a problem for people to deal with it because they have multiple knowledge-intensive constraints that they use. For example, transitivity. People know that if A happens before B and B happens before C, then A happened before C. And I'm showing here an example of something like this in the graph. And people also have some prior knowledge on events that typically precede other events. So if I give you a piece of text on the bottom right here and I say more than 10 people have something, police said, a car, something, on Friday in a group of men, and I ask you which happened first, event 1 or event 2, you have no clue. But if I put the lexical item there, now you know because you have a lot of prior knowledge on these two. So the computational challenge for us is the reasoning one, really. How to exploit these declarative and statistical expectations. The transitivity constraint is an example of a hard constraint, and the priors as an example of soft constraints. And you know, many, many years ago, we developed a framework for something that today people call constraint decoding. And the framework there was called integer linear programming inference for NLP. The idea was to put together an objective function that allows us to put variables as output of models. In this case, it would be predictions for order of events. It allows us to put hard constraints and allows us to put soft constraints as a way to regularize this objective. And then you can solve for these kind of things. And this is still a valid framework, a valid way to think about these things, even though it's more than 15 years old. And you can place this way of thinking about enforcing constraints on the output also in the context of neural networks. In this case, we are doing it in the context of additional constraints. We think about an additional relation. We think both about temporal relations, sub-event relations, coreference relations, and you can model each one of them using a neural network. And you can then enforce logical constraints by converting declarative constraints into differentiable learning objectives. And again, I'm not going to give the details. There's a couple of papers that I'm listing there that have done this. But the bottom line is that we have to do something like this as a way to put modules together. There is no way to reason, or it's difficult to reason globally on everything we want to do. And the global reasoning also is very sparse, but we can reason component-wise and then put things together using these kind of approaches. The second approach to putting things together that I want to address, again, think about will we make it to dinner before the movie as a running example, has to do with, again, the composition and composing things into events. So I'm going to give this example. As you can see, all my examples have to do with food. In this case, this is a typical dish for Chicago. I got a free plane ticket to Chicago last week and had some local dish, deep dish pizza. Now we want to be able to reason about it. We know that we got the tickets. I want to ask the question whether we got the ticket before we ate the deep dish pizza. And in order to reason about it, you need to know that there is some event flying to Chicago that happened in between. And I guess we all know this, but it's not written in the text. In order to understand that these are the relations, we need to know what is the end time of flying to Chicago. Is it before the beginning of eating deep dish pizza or after it? So in order to be able to reason about order of events, also in the presence of implicit events, think about the parking case in the first example that I've given you, or flying to Chicago in this example. We develop a new temporal closure inference dataset that basically, think about it as a textual entailment dataset. The premise is a story, and then we generated a hypothesis of the type fly starts before we had pizza, or fly ends after we had pizza. And we generated this, and I'm not going to get into the details of how we generated this. So it's a combination of using Amazon Turkers and some randomly selected comparators. And this allows us to study the question of putting together common sense component, temporal common sense component that I discussed the acquisition of before. So the first component is, of course, to develop this common sense component. And I talked about the pattern-based pre-trained temporal model that we had. And then the question is, how do we do this temporal reasoning? And I'm going to focus here on computing end time, because this is really what's important here to decide whether we ate the pizza in Chicago or not. But it's actually very easy, because we all know that end time is start time plus duration. So how do we encode this into models and deal with it? So we really develop a generic reasoning model without any task-specific instances, and we show that we can also fine-tune it on the specific data set. But even without this, we actually get very nice results. And I'm just going to give the kind of a hint of how this is going. So really, we think about it as a general way to educate submodules, and then do some data-specific fine-tuning. So we start with the fine-tune language models, and then we do task-specific pre-training to develop some experts. In this case, and once we have these experts, and the experts could be an expert in identifying duration or identifying the start time of events. And once we do this, and in this case, these are indeed the two experts that we have. One of them is an expert in identifying start time of event in the text, and the second expert is an expert that identifies the duration of phrase. And it's exactly the same language model that I described before that we did for multiple temporal aspects. And once we do this, we want to be able to put these two together to reason and provide end time. The idea is that in most cases in text, start time is much easier to identify than end time, because that's the way human authors write text. We specify the start time. We rarely specify the end time, because the assumption of the authors is that people know that. People can figure it out. But we have to be able to reason about it just like people do. So the idea is that, again, we have these two components. The basic step here is this textual entailment component. Given the context, I want to know whether the context entails that fly starts or ends before or after eating pizza. So that has two components. If the comparator is start, it's an easy problem, right? So we just need to determine whether the distance between this beginning of events is positive, which means E1 happened before E2, or otherwise it's after. And the second one is difficult because if the comparator is end, I want to compare the end times of the events. That requires reasoning. I need to know that the distance between the start times minus the duration is positive. If that's the case, then it's before, otherwise it's after. And this is the difficult time. And we basically developed this architecture where what you see here are the two components for duration on the left and for the distance on the right. And then we can put this together. And I'm not going to go into the details. The thing is that we can do one of two things. We can just do it in a zero-shot way, or we can fine-tune this architecture. And in both cases, we can show that the results are very good. Of course, fine-tuning improves the results. But even in a zero-shot way, the results that we get is much better than a standard language model trained on this data set. Okay, I'm not going to show results.
Sorry, Dan. Sorry
yes.
to interrupt. I'm enjoying the talk greatly, but I think we only have a few minutes left.
Yeah, I'm going to summarize.
Okay. Thank you.
So, okay, I wanted to talk a little bit about supervision, and I will not talk about it. The basic thing that I wanted to say is that we have to think about how to supervise these kind of systems, and the composition is key to supervise it. And there are multiple things to say about it. And basically, the idea is that we typically cannot think about it as only end-to-end, because end-to-end supervision here is way too weak. There's so many intermediate decisions that we have to deal with, and I'm highlighting some of them here, but I'm not going to get into it. So I'm going to skip kind of the last slide where I wanted to talk about supervision. I'm happy to address this in questions, and I'm going to conclude. So basically, the goal of my talk was to argue that we must think more about reasoning in order to support better communication, which is our goal. And our theories for learning are good for many things, but are not sufficient to deal with the sparse, interesting world. And we really need a theory of reasoning in order to handle it. So I try to address some of the key issues. I talked about knowledge. I talked about compositionality, how to decompose and how to put things together. I didn't talk enough about supervision. I think about supervision with incidental supervision, which is another paper that I've written addressing these issues as a key here. But there are many other issues that we have to think about if we want to kind of move forward in more robust reasoning about natural language decision. And I'm going to stop here and happy to take questions if there's time.
Thanks, Dan. I think we have some time for questions. So anyone who wants to ask, just I think you can take the mic, unmute yourself. Rodrigo is there. You can talk.
Yeah. Can you hear me?
Yes.
Yes.
Okay, thank Dan. It was a very nice presentation. Many things to talk about, but I restrict myself to just a very simple and specific question. Not before mentioning that I'm very happy always to have citations, philosophers as citations, such as Kripke. And I also was thinking about the Hans Kamp work on discourse representation theory. And that includes many of the concepts that you presented here. And I think that in NLP also there is a very nice tradition on that line, which I think is quite relevant for what you are doing. I think it's also an interesting work. And my question was, so in the TACO dataset that you have presented and in the way you are modeling temporality, you are not including any kind of normalization, right? So you are not normalizing temporal expressions with respect to a specific, say, creation time of the document that you are working with? Because
we actually are doing it. We did not do it in this specific work because here we just cared about cases where time is not explicitly mentioned, which is the case in most events. You just want to know whether something happens before or after. when the time is not explicitly mentioned. If the time is explicitly mentioned, the problem is easier, and it requires, as you say, normalization. So we have work that we've done a couple of years ago on normalizing text relative to DCT.
Nice. And do you include also this information for pre-training the language model?
No, not in the original paper that I mentioned. We have now work in progress where we are doing that too. That's a very good point. So the reason is that most of the event text have very, very minimal mention of explicit times. But I think in general, what you suggest is essential. It has to be incorporated.
Okay, thanks a lot, Dan. Cheers.
Thank you. Any other question? Yes, Iker, go ahead. Yes, Iker, I see your hand raised.
Can you hear me now?
Yes.
Yeah.
Okay. Hi, Dan. My name is Iker. I'm looking forward to work with you in September. My question is, this week, two huge models has been presented, PALM and DALI, and these models seem to be able to understand tasks written in natural language. Do you think that these kind of models are a step forward for reasoning, or we need something more than a lot of text and a lot of parameters?
So you're talking about the 540 billion parameter model?
Yes, because there are some examples and the model seems to understand like that you can ask something to the model and it understands it.
Yeah. So I haven't read the whole paper carefully, but I think it's very interesting. What I found mostly interesting there is the chain of thought prompting that they do, which basically trains the model, essentially trains the model in decomposing the reasoning process. I think it still lacks a lot, but it's certainly a very interesting step forward because it shows that the model can kind of follow these reasoning steps a little bit. So my answer is twofold. First of all, I think it's really interesting. I think that prompt engineering there is done very well and gives a lot of new ideas. Nevertheless, I would take this a little bit with a grain of salt, because you can always show nice examples, but as you start quantifying this, you will see that it's actually very, very brittle. You change one thing in the input, the results drop. I haven't played with the 540 billion parameter model, but I played with smaller models, say 20 billion parameter or something like this. And there you can see that it's extremely brittle. So while it gives a lot of good ideas, I think there's a lot of stuff to do there still.
Thank you.
I have a question of my own. Well, I don't know if it's a question because, well, you touch on so many things and actually which are very complex. So in a way, I'm very happy about this talk because some people seem to think that deep learning, which has allowed tremendous progress for NLP, is sufficient for solving NLP, which I think your talk very clearly shows that is not sufficient because language models don't reason properly. And there are things that they are not going to learn by themselves. But it's also true that when people have started to build common sense knowledge bases in the past, like the Psych project with multi-million investment, they kind of failed because it's a gigantic task, right, to formalize all knowledge and reasoning. So then I guess there are two ways ahead. I think you have in general, and correct me if I don't say this correctly, but there is a solution, for instance, where there is a knowledge base, a small knowledge base about, say, restaurants, opening times, and some handwritten rules about the domain, where natural language understanding is just the task of mapping from natural language to in a semantic parsing task to the formalization of the knowledge base. I think that you had one slide in the beginning. I guess that route would work for small domains which can be formalized by hand, right? And from what I understand, the problem is that it's not possible to scale this up. So there are many small domains where you can do this, but in the end, it's really difficult to scale this up. So the second solution, which is not to code everything by hand, is to use some heuristics and some knowledge about the domain to let the language models or some other architecture learn the common sense for the task. So is this more or less a good summary of what you have presented? Or?
Yeah, I think it is. So I think that it's a combination. So I completely agree that there is no way to write down everything. And there's also an issue of representation. How do we represent the common sense information? And I think that bottom line is that it has to be some kind of a distributional representation. And the suggestion that we've given of how to represent temporal common sense is, I mean, not necessarily the only solution, but I think the solution will have to be something like that, a distributional representation. And it will have to be acquired somehow. But I think that that's just one component, as you said. And the second component will have to be how to convey to the system additional information. And when I talk here about some declarative information, so we have to be able to inform the system about some soft or hard constraints and figure out ways to incorporate this. And again, the issue is representation. I mean, how do we represent this knowledge and in a way that facilitates incorporating it into the system? And I think, again, there are many ways of doing it. So there are several suggestions in the literature. We've done this recently by essentially putting together multiple networks, if you want, and then changing the global objective to include declarative constraints. There could be many other ways of doing it, but there has to be ways to inform systems about things that they will never see, or things that are very, very rare. So yeah, so I think the summary that you gave, I think is in agreement of the way I think about it today.
Okay, thanks. We have time for, I think, another question. So, Lifeng, go ahead.
Can you hear me?
Yes.
Yeah. Thanks, Dan, for the talk. That's very nice. Exactly on these slides, I'm wondering what's the logic of putting by RSTM layer after this robot embedding, and what this MRP representing for?
So what is, say it again, I couldn't hear the last thing.
I was wondering what is logic to put the by RSTM layer after this robot embedding, and then this MLP is representing for what component?
So the ILP component is basically a formulation. You think about it as you have an objective and you have constraints and so on. The implementation itself does not have to run an ILP solver. I think really the significance of this is that it's easy to formulate problems this way. The solution itself actually takes the constraints and represents them differently in a soft way. basically by changing the objective, you can take any logical constraints and represent it as objective, and then you put it as a top layer, if you want, of the network, and you can train it. You can train end-to-end with this differentiable new learning objective. So we don't implement ILP. We just formulate the problem as an ILP and then convert it to the objective. Is that answering the question?
Yeah, and the connection between BiRSTM layer and Roberta, why does this make sense?
Well, it's one implementation of this, not necessarily the only implementation of this. But the idea here is that what we can do, or what's natural to do, is to think about pairs of events and learn the relation between pairs of events. But somehow you need to be able to put together multiple pairs and think about them globally. So that's the way we figured out to model this, not necessarily the only way to do it. So I think that's a technical detail that we found that this is a useful solution. You may think about a better way to model this. But I think the conceptual thing is that you have multiple models that deal with different components of the text, but eventually you want to be able to reason globally about all of these. And the left network doesn't see the events that the right network sees. And we need somehow to figure out how to bridge this gap.
Thanks, Remember. I want to ask a general question for suggestion, if I may. First greeting from Manchester. I'm just moved here, and for this question answering, and you have give examples, and also the hosting chair also mentioned this common sense knowledge and temporal common sense knowledge. How about is there any dataset focusing on health text domain? And for healthcare domain data such as question answering or information extraction, do you have any suggestions?
Okay, first of all, I think it's a great domain.
Yeah.
So we actually started recently to work in this domain. In fact, you can find on my website a paper that just appeared in JAMIA, where we look at some kind of temporal reasoning in the medical domain. The application is epilepsy. We're trying to understand the time of previous episodes of epilepsy from electronic health records of patients. And there's a new paper coming up, probably will be there on the website in the next few days, that deals with some sort of temporal reasoning in this medical domain. So, you're very welcome to look at it, and I'm happy to discuss this later.
That's great. Thanks very much.
Okay, thank you all. Thank you, Dan, for your time and your patience with the questions and answers. And I think this is more about research, a research program, because you cover a lot of terrain here, but there's plenty of work in this area, so it's really exciting. So thank you very much. I want to remind the rest that there will be another webinar in 1 month. And you can go to the website and get the details. Okay, so thank you. And
yeah, thanks, Eneko. Thanks, everyone. Bye-bye.
Okay, bye.
Thank you.